Am I audible to all of you guys? Okay, cool. Give me a minute, guys. Okay, guys. So let me share my screen. Is my screen is up for you guys? Okay, yeah. Sorry for the delay, guys. There was some issue. Okay, cool. So is my screen is up for you guys? Great. So let's begin with the session, guys. So I guess yesterday we saw the basics and some terminologies related to the neural network part, and we also saw how to build a typical neural network architecture using Python, right? So there we have introduced like TensorFlow and Keras. So today we are going to understand how the backend calculation is happening when you are designing any kind of a neural network architecture. How the calculation or information is flowing from input layer to output layer, and how optimizer will optimize the weights so that the error will get reduced. Okay, so this is the agenda for today's session. And once we complete this backend calculation and processing, then we will also introduce the things related to the RNN. Okay. So before starting with the session, guys, any doubt or any queries till last session? Anyone? Okay, cool. No queries. So before getting into the backend calculation, there are some prerequisites. So the thing is, guys, I'm sure all of you guys have studied in your 10th or 12th. There is something called as a differential calculus, right? Where you have studied the things related to the like differentiation in the mathematics part. Let me just remind you a couple of concepts related to the differentiation, and then we will come to our main topic. So if I talk about, guys, straight line equation. So the straight line equation is simply y is equals to mx plus c, right? Can you guys tell me what is this m here? What is this m? Right, it's the slope of the line. And how this slope is being calculated? It is being calculated as del y by del x, right? Which is nothing but y2 minus y1 upon x2 minus x1. You can also write this slope in terms of the differential equation terms. So like dy by dx, right? I'm just reminding you all of these small concepts so that it will be easier for you guys to understand the backend calculation for a neural network architecture, right? So this dy by dx is nothing but it is the differentiation of this y with respect to the variable x. Okay. Yes, guys. So it is a slope or gradient, right? So let me just remind you a couple of formulas for the differentiation. So let's suppose we have a y is equals to x cube, and we want to differentiate y with respect to x. So it will be dy by dx. So what is the outcome? So outcome, it will follow this particular rule. If you want to differentiate something called x to the power n with respect to x, so it will be n multiplied by x to the power n minus 1, right? So what is the n here? N is the power of this x. So that is 3 multiplied by x to the power n minus 1. 3 minus 1, that is 2, right? A simple calculation formula. And then let's suppose, guys, we have a function called y is equals to 2x square plus 1. And if I ask you to differentiate this function, y is equals to 2x square plus 1 with respect to x, so dy by dx is nothing but 2 is a constant, and then x to the power n, it is something like n multiplied by x to the power n minus 1. 2 minus 1 is 1. Plus differentiation of the constant will always be 0, right? So it will be 4x. Okay. I'm sure all of these things you guys remember, right? And there is one very important rule in the calculus. That is something we calling as a chain rule of derivatives. So what is this chain rule of derivative? So let's suppose you have a y, which is a function of x. So let's say it is a function of z, and z is a function of x, right? So y is a function of z, and z is a function of x. And let's suppose I want to calculate dy by dx. That means differentiation of y with respect to x. But y is not the direct function of x. Y is a function of z, and z is a function of x. So here comes the rule of chain rule of derivatives. So that means first take the differentiation of y with respect to the z, and then take the differentiation of z with respect to x. So that will be dy by dz into dz by dx. Right? This is something we are calling as a chain rule of derivation or derivative, right? Okay, cool. So I guess you guys recall a couple of concepts with respect to the differential calculus, right? Now let's start with how the internal processing is being done and what are the different things will be there. Okay, so the objective is two things. First part, we will going to discuss how the information is flowing from input layer to output layer. And the second thing we will be discussing how the optimizer will optimize the weights, right? So let's begin with the session, guys. So we are going to start with the very simple neural network. So let's say, guys, this is our neural network, what we are going to take into this consideration. In this neural network, we have a one input layer, one output layer, and one hidden layer. And for all the layers, we have two nodes, right? And this is something we have a bias value. So as we have already discussed, for each and every input connection, we have some weights available. So let's say these are the values of the weights for all of these connections. So like for this connection, weight value is W1. Let's say for this connection, weight value is W2. For this connection, weight is W3. For this connection, weight is W4, W5, W6, W7, W8. And this is the bias value, right? So here also we have some weight values. So what we are going to do, we will take some input values, right? And we will also consider some output values. So let me just show you what I'm explaining you. Yeah. So let's suppose, guys, it is given that the input for these nodes will be these two values. That means 0.05 is the input for I1, which is this one. 0.10 is the input for node I2. And it is given that the final output is this one. So this is the actual value of the output. This is not the value predicted by this neural network. This is the actual value which I know, right? Now, what we are going to do here, if this is the input for neural network, then how neural network will produce the output, and then whatever output is being produced by neural network, we will compare this output with respect to the actual value of the output, right? And then what will be the error? Error is nothing but the difference between whatever output is produced by neural network and the actual. Okay. Is that clear, guys? Cool. So I hope everyone is clear what we are going to perform here. So, okay, let's start. So guys, how neural network starts working. So if you recall the discussion over neural networks, so there we have discussed, first of all, it will assign some random value of the weights for all of these connections. So whatever the value of weights you are seeing here, 0.15, 0.20, 0.25, and so on, these are some random value of weights from which the neural network will start processing. Okay. Now let's see how the processing is going to happen and how these nodes will do the calculation. Okay, so this is what we have. Okay, so let's see. Let's consider the node H1 because the processing will start from layer 1, right? The nodes of the input layer, they don't perform any kind of a processing. They will only contain the input data. So if I consider this node H1, so what this node H1 will do, it will perform two functions, part 1 and part 2. So in the first part, it will perform the adder operation, and whatever is the output of the adder, that will be the input for your activation function, right? So let's see, guys, what will be the output of adder function for node H1. So if you see for node H1, how many inputs are there? This is first input. And what is the value of this input? 0.05 with a weight value 0.15. This is the second input node H1 is getting. And what is the input value? 0.10 with a weight value as 0.20, right? And there is a bias value for this node H1, which is 0.35. So what is the output of the adder function? It will be I1 multiplied by weight W1 plus I2 multiplied by weight W2 plus bias value. So this is what we are getting, net H1, which is the output of adder function for H1 node, 0.15 multiplied by 0.05, this weight getting multiplied by this input, plus 0.2 getting multiplied by 0.1, 0.2 weight W2 getting multiplied with input 2, plus bias value, right? So this is the output for adder function for node H1. Now this output will be the input for activation function for node H1, right? And let's suppose we are going to consider the activation function as a sigmoid, right? So one of the activation function is sigmoid, which has the formula 1 upon 1 plus e to the power minus x. This is the formula for the sigmoid activation function. So for simplicity purpose, we are going to take this sigmoid as the activation function. And what is this x? This x is nothing but the output from the adder function. So if you see here, the final output from this H1 node will be the output from this particular function. So the output of node H1 will be 1 upon 1 plus e to the power minus net of H1. And what is the value of net of H1? 0.3775. If you put this value and do the calculation, you will get this as the final output for node H1, right? So from the node H1, what value is being generated? So it's a 0.593. Now this value is being passed to O1 and O2, right? This is the output of node H1. And the same process H2 will perform the adder function and activation function, right? So for node H2, this is first input and this is the second input. The weight value are 0.25, 0.30. If you do the calculation, you will get the value as a 0.596 as the final output value from node H2. 0.596. And this value will get input to the node O1 and O2. Is that clear, guys? How the node H1 and H2 is generating the outputs? Any questions, anyone? Okay, great. Now see, so we have an output for node H1, output for node H2. And we can also perform the same functionality for node O1 and O2, right? The nodes for the output layer. First one will be the adder function. Second one will be the activation function, right? So you can also get the output from these two nodes O1 and O2. So what will the output for node O1? So first consider the adder function output for node O1, which will be 0.4 multiplied with the H1 value plus 0.45, this particular weight multiplied with the H2 value plus bias value, which is 0.6. So this is the final like adder function output for node O1. And this output will be the input for activation function of node O1, which is a sigma. So this is the final output what we are getting from node O1. And similarly, this is the final output what we are getting from node O2. So now what we are getting, final output 0.75 13, and for node O2 0.7729. So guys, this is the output what we are getting from neural network. So this is the prediction from the neural network. But what is the actual value? This is the actual value. So it has been given to us that actual output value is this one. But what this neural network is producing as the output, these values. So can we calculate the error, the difference between these two values and these two values, right? So that will be the error for this neural network. Let me just show you. Now, to calculate the error for the neural network, there are multiple kind of errors are available, right? So what we are going to do, we are going to take one particular kind of error, which is known as a squared error function. So what is the squared error function? This is the formula for the squared error function. Summation of half of target value minus output value square. So this we are going to apply for node O1 and O2. And the total error is nothing but error for node O1 plus error for node O2. So let's calculate the error at node O1. So what is the error at node O1? Half of target value is nothing but the actual value. Actual value was given as 0.01 minus what is the predicted value for at node O1? 0.7513 whole square multiplied by half. So this is the error which is present at node O1 considering the squared error function. As I told you, there are a lot of error functions are available. You can take the absolute error. You can also take the percentage of error. You can also take the squared error. There are a lot of error functions are available. So let's consider the squared error function. And based upon that, this is the error what we are getting at node O1. Similarly, we can also calculate the error at node O2. Let's suppose this is the error what we are getting at node O2. So what is the final error for this particular network? Sum of this error plus this error, right? So the total error is nothing but error at node O1 plus error at node O2. Just sum these two values. So you will get 0.2983. This is the final error for this particular neural network, considering these weight values, right? Is that clear, guys? How we are calculating the error? Any doubt or any questions up to this part, anyone? Colleagues, you can consider this bias just like a constant, right? Just consider this bias values as a constant one. Okay. But apart from that, guys, is that clear, guys, how the calculation is being done from input layer to output layer and how we are calculating the error part? Yes, Kola, you can change this bias values. So as I told you initially, the network will assign some random values. So let's consider these are some random values is being assigned in between 0 to 1. So this is the first iteration how we are executing this network. Now, once the neural network will get the error for the first iteration, which is this one, here comes the role of optimizer. Now, optimizer will try to minimize this error, right? How it will minimize? Just by tuning these weights values. Okay. Whatever bias weights or these weights are there, just by tuning this weights value, optimizer will try to minimize this error value. Are these formulas known as the activation function? Which formula, Himanshu? Which formula you are talking about? Yes, Himanshu. This is the formula for the activation function. Let me just show you. You can see here, guys. I have taken an example with sigmoid activation function, which has the formula like this. Y is equals to 1 upon 1 plus e to the power minus x. If you take activation function as a tan h, the formula will be this. If you take ReLU as activation function, the formula will be like this. For max out, formula like this, right? So for each and every activation function, there is some logic or formula is being associated. So here I have taken sigmoid as the activation function. Okay. Yeah. Cool. So up to this point, guys, we have saw that how a particular execution is being performed at the backend from the neural network and how it will generate the outcome and how the error is being calculated. And let me again remind you, whatever these weights value you are seeing, these are some random weight values which are used to initialize this network. So after getting this total error for this network, now here comes the role of optimizer. What optimizer will do, it will try to minimize this error value by tuning this weights value. So it will try to get the optimum value of these weights so that the error will be minimum. Right? Let's see how it will perform. Okay. So this is the total error what we are getting for this network. Total error means error at node O1 plus error at node O2. Now we are going to see how the error is being minimized with the help of a very basic optimizer and very useful, which is called as the gradient descent optimization technique. Gradient descent optimization technique, right? And guys, please remember this point. This is very important. Throughout your deep learning or AI based approaches, whatever model you are using, doesn't matter whatever model you are using, whether you're using simple neural network, ANN model, RNN, LSTM, or any kind of a neural network model, when it comes to optimize these weights value, each and every optimizer will follow backward propagation technique to optimize these weights so that the error will reduce. Each and every optimizer will follow backward propagation technique. Now, what is the meaning of backward propagation technique? That means what optimizer will do, it will start optimizing the weights value for those connections first, which are closer to the output layer. So this is my output layer. Now, can you guys tell me for this network, what are the weights which are closer to the output layer? Whether these are the W1, W2, W3, W4 or W5, W6, W7, W8. What do you think? Which are the weights closer to the output layer? Any answers, guys? Right. W5, W6, W7, and W8. So these are the weights which are closer to the output layer, right? Along with this bias value. So what optimizer will do? It will first optimize these set of weights, right? It will first optimize these set of weights without changing these weights values. Once it will optimize these set of weights, then it will optimize the weights which are, you know, closer to this particular layer. That means this particular weights, set of weights. And then if you have another, layer, then it will optimize those layer weights. That means when it comes to the weight optimization, so the weight optimization is being performed from output layer to the input layer in this direction. That is the backward direction. That's why the method is called as a back propagation. Backward direction. That means from output layer to input layer. So first, these layer weights will be optimized. Then these layer weights will be optimized and so on. And the method is called as a back propagation. Guys, this term is very important. And you name any kind of a deep learning model or AI-based model, each and every model will optimize the weight using the backward propagation or back propagation method. So there are two things. The information is flowing from input layer to output layer in feed forward manner, in a forward direction. Forward direction. The information is flowing in forward direction, and the weights is being optimized in backward direction. So here, weight optimization. In backward direction or back propagation method. Right? And this is the, how information is flowing in forward direction. That means all the calculation is being started from input layer through hidden layer through output layer. And when it comes to the weight optimization starts from output layer to hidden layer and then towards input layer. Is that clear, guys? This part? Any doubt to understand this back propagation technique? Anyone? Cool. So this is very important term, back propagation, right? And then, guys, based upon whatever technique you adopt, based upon that like optimization technique, it will optimize the weight value. Now let's see how the weights is being optimized. So if you see, guys, the total error is 0.29. Let's suppose it's a E total. And as I told you, first of all, these set of weights is being optimized. So let's see one of the weight, which is W5, right? Now to optimize this error with respect to W5 weight, what it will do, it will calculate the gradient of the error. And what is the gradient? Gradient is nothing but the simple differentiation. Differentiation of total error with respect to W5, right? But see here, guys. This is your output node O1. This is, here we have a E total. And here we have a weight W5. So to find the gradient of error with respect to W5, so that the W5 will get adjusted or we will get the optimum value of this W5. So to get this gradient, you can't directly get the gradient. The reason being, the total error is not a direct function of W5. So total error is a function of activation function. So from activation function only you are getting the output of the total error, right? And this activation function is a function of this adder function. This adder function depends upon this weight W5, right? So to find this gradient, here comes the role of chain rule of derivation. So DE total by DW5, that means this particular derivative part will get broken into this chain derivation rule, right? So to find the del E total by del W5, it will be first of all del E total with respect to del of activation function, whatever activation function you are using, multiplied by del of activation function with respect to del of whatever adder function you are using, and then your adder function is a will depend upon weight W5. So this calculation is being present at the backend when it comes to the weight updation. So this is with respect to W5. The same thing it will do for W6, W7, W8, right? So this calculation, this chain rule, derivative part will be there if you are talking about the weights updation. So this is something with respect to W5. Now let's see, guys, if you want to update the W1, so how E total will update the W1 and how the gradient will be calculated. So del of E total with respect to del of W1. So here we have a E total. So first of all, E total will be a function of activation function for output one node. Output node one activation function depends upon adder function output for output one node. Adder function output depends upon W5. W5 depends upon activation function of node H1. Activation function of node H1 depends upon adder function output of node H1. Adder function output depends upon weight W1. So these many gradients will get calculated at the backend to update this weight W1. And this is, guys, very simple neural network where we have only one hidden layer. Let's suppose we have a hidden layer where we have a neural network where we have, let's say, 5 hidden layers. So this is your input layer. Let's say this is first hidden layer, second hidden layer, third hidden layer, fourth hidden layer, fifth hidden layer, and here you have a output layer. So in this case, let's say hidden layer 1, hidden layer 2, hidden layer 3, hidden layer 4, hidden layer 5. So in this case, guys, if you want to, optimize the weight values, and let's say you want to optimize these set of weights or these set of weights. So you can consider how many, gradients are being calculated at the backend to update these set of weights or these set of weights or these set of weights, right? So there are too many gradients are being, calculated at the backend to adjust or to optimize the weight values. Is the concept is clear, guys, how the weights are being adjusted and what is the back propagation technique? Any issue to understand this concept, guys? Anyone? Cool. Yeah. So this is one part, guys, which I need to discuss with you. So what is the back propagation and how the weights are being adjusted? Now we will again come back to this, weight adjusting part with respect to this gradient calculation, because there is some issue while this, gradient are being calculated with RNN or ANN. You can consider any one of them. So that is something I will discuss probably in today's or tomorrow's session, right? So we will again come back to this point. Okay, so this is one part, guys. Okay. So up to this point, guys, we have understood end-to-end neural network architecture, how to how to build a neural network architecture, what are the different terminologies are there, what is a dropout layer, what is the back propagation, why we call this one as a sequential neural network, and so on. Right. So with this, guys, let's focus towards our main topic, which is a generative AI. And when it comes to the generative AI, the basic building block for the generative AI is the RNN models, which is a recurrent neural network, right? So you name any kind of a generative AI tools or techniques. So almost all kind of a techniques are built over some kind of a RNN model or architecture. So it's very important to understand recurrent neural network, which is the RNN network, so that you can grab the background architecture for any kind of a generative AI techniques, right? So let me start with introduction to RNN, and then we will move slowly towards some other concepts of the generative AI, right? So meanwhile, guys, any questions or any queries, anyone? Let me also check with YouTube, guys. Okay, guys. So no queries, right? So let me start with the RNN, which is a recurrent neural network. Is my screen is up for you guys? I have an option on my desktop screen, Zoom now, AI companion. What is it is? Tanishka, I have no idea what is this option, right? Okay. So let's begin with, guys, the backbone of any kind of a generative AI tools or techniques, which is the RNN. So as I told you, to take any kind of a generative AI model or tool. So if you see the background architecture for that kind of a tool or model, so most probably, like most of the cases, you will get some kind of a RNN network architecture will be there, or some modified form of the RNN neural network, right? So RNN stands for the recurrent neural network. So yesterday, guys, we like I showed you, uh, top view of the deep learning domain, where you can see how the things are arranged. So we saw something called ANN, artificial neural network, that is for regression and classification related tasks, regression and classification modeling. We have a artificial neural network. We have a convolutional neural network for image processing or video data analysis. And you can also use CNN, for time series, or even you can also use CNN for the text data analytics. But the majorly we use CNN kind of architecture, which is a convolutional neural network for image or video analysis. Then we have a RNN, recurrent neural network, and that is used for sequential data analysis. And under the sequential data, we have the time series forecasting, and we have this text data analytics, right? So these two comes under the sequence data analysis. That means sequential processing, right? So in that way, things are arranged. So now we are going to understand a recurrent neural network, which is the RNN. So let's start. So to understand the RNN, let me just explain you one very basic and very important understanding of the deep learning. So as we guys know, deep learning or AI will try to mimic the human behavior, right? And that's why how the neuron in our brain performs, the similar fashion, we have the neural networks architecture in deep learning, right? Let's see another aspect of our brain's functionality with these kind of networks. So guys, this is a typical brain architecture what we have. So in this brain architecture, we have two things. One is a cerebrum, another one is a cerebellum. So whatever this, underneath portion you are seeing, this particular thing is called as a cerebellum, right? And then this big part of this brain is called as a cerebrum. So with respect to this cerebrum, we have a four different domains or four different, sectors in our brain. This part is called as a frontal lobe, this blue portion. This green portion we are calling as a temporal lobe. This yellow portion we are calling as a parietal lobe. And then this pink one is called as a occipital lobe. So that means we have a four lobes: temporal lobe, frontal lobe, occipital lobe, and parietal lobe. Now, why we are discussing this architecture or this particular, brains part? The reason being the manner how our brain, these lobes performs, the same manner we have our neural network architecture, different neural network architecture. For example, whatever this temporal lobe we have, the functionality of this temporal lobe is being transformed into artificial neural network. So if you build NN kind of a model, the model will have a similar kind of a functionality as a temporal lobe, right? Whatever we have this occipital lobe. So this is this is a part of a human brain which will try to capture the images or videos. Whatever we see through our eyes, this part will try to memorize those images or videos, right? So this functionality is being replicated with the convolutional neural network, which will perform the image analysis or video processing. Okay. Now, what about this frontal lobe you are seeing? This frontal lobe is also called as a short-term memory. Short-term memory. This functionality is being replicated with the neural network called RNN, recurrent neural network, right? So whatever architecture we have over this recurrent neural network, it is having the similar kind of a functionality what we have in a frontal lobe. That is a short-term memory. That means it will try to memorize, recent incidents. That's why we are calling it as a short-term memory. And similar kind of a concept is being implemented in the RNN. And then we have something called parietal lobe. This particular part of the brain will try to, they will perform the functionalities like sensitivity or sensations, these kind of things. So as of now, we don't have any kind of a AI based, architecture which can replicate this kind of a behavior. So the behavior related to the sensations or feelings. So this kind of a behavior is not being replicated as of now. For rest of the three parts, we have replicated these three parts in neural network architecture, right? Let me just go through these slides also. Yeah. So for temporal lobe, the same thing will be, we have replicated like NN architecture. Frontal lobe, it is like a short-term memory. So RNNs are also like a short-term memory. So what they will do, like you will learn that they can remember the things that just happened. So with the same concept, the RNN is being designed. Like in a previous couple of observations and apply that learning in a going forward. So that is in our human brain, we have a frontal lobe that will perform the similar functionality. And in deep learning architecture, we have a RNN, recurrent neural network. Then as I told you, we have an occipital lobe. So it is being replicated as a CNN, which will responsible for the computer vision, recognition of the images, objects. So this kind of a thing is being replicated with the neural network called CNN. And then parietal lobe. So this kind of a lobe is responsible for the sensations, perceptions, constructing a spatial coordination system. So these kind of things are not being, implemented in a neural network as of now. But researchers are working over this particular domain also. So this is how that why we are calling AI is nothing but is to mimic the human behavior. Why we are calling this? The reason being, we have we have built the architectures which can, replicate the functionality of brain like this. So this is one part, so that you guys can relate the things with our brain's functionality. Okay. So yeah. So after this part, guys, we understood how the things are arranged with respect to our human brain behavior. Okay. Now let's see how the RNN architecture will be, built by using the basic neural network architecture. So you guys need to follow a couple of steps, to build a RNN architecture. Let me just show you through these diagrams. So let's suppose, guys, we have this kind of a neural network architecture, and this is a very straightforward neural network architecture where we have a one input layer, one output layer, and one hidden layer. So in the input layer, we have a 3 nodes. In the output layer, we have a 2 nodes. In the hidden layer, we have a 4 nodes. Okay, and these are the different connections. So if this is the neural network is available with you, how you can design the recurrent neural network or RNN? Let's see. And this is the guys, this is a pictorial representation. When it comes to the like designing the neural network in a practical sense, so there we have a different functions. Okay, so this is some pictorial representation just to understand how RNN is being designed. So if this is the neural network we have, then follow a couple of steps. Like, first of all, just squeeze this network layer by layer, just squeeze it. So if you squeeze this network, so all of these 3 input layer nodes will become only one node, right? It's not like there is only one node. So all other nodes are at the back side of this node. So you can see only one node, but 2 nodes will be at the back side. And then try to squeeze all of these connections, all of these nodes as a single node, and all of these 2 nodes as a single node. So let me just show you what does that mean. So it's like this. Just squeeze this network, right? So it's not like we have only one node in the input layer. We have 3 nodes, but the 2 nodes at the back side of these 2. That's why we can see in the front only one node. And just squeeze all the connections, all of the nodes of the hidden layer. So it's not like we have only one hidden layer node. We have other nodes at the back side of this particular node. But since we are seeing from the front, we can see only one node. Same for the output layer. Yeah, Mohit, for understanding purpose, you can say that, right? So if you squeeze it completely, it will look like this, right? So just squash it, and if you see from the front, you can only see one node of the input layer, one connection, one node of the hidden layer, one connection, and one node of the output layer. But it's not like there is only one node. All other nodes at the back side of these nodes. And all other connections are at the back side of this particular connection, right? And then just make it as a vertical diagram. So just, rotate it in a vertical manner. And then here comes the role of the word called recurrent. What is the full form for RNN? It's a recurrent neural network. So this word recurrent, the recurrent means, the word recurrent indicates that there will be some feedback connection. feedback connection, which we are calling it as a memory, right? Feedback connection or memory. So this is the meaning of this word called recurrent. That means somewhere we have the feedback connection, the connection back to its input. That is something we are calling as a feedback connection. So if you see here, guys, this is my input layer nodes, and this is the this is the input which is fed to this hidden layer, right? This is the hidden layer. From this, we are getting the output from the hidden layer, which is the input to this output layer. So here we have the feedback connection or the memory element for this hidden layer output. So whatever output is being generated from here, that output is fed back to the hidden layer input again. Let me just show you what that does mean. Yeah. So whatever output is being generated by this hidden layer nodes, that output is being fed to the next layer node, as well as the same output is fed to the hidden layer input. So at the hidden layer input, we have two inputs. One is from the input layer, another one is from the output of the hidden layer. So this connection, this feedback connection is called as a recurrent network, right? That's why we are calling it as a recurrent. And since we are storing the output of the hidden layer, right, in this network, that's why it will memorize the output. So it will memorize the output of the hidden layer. So this is the representation of RNN network, recurrent neural network representation. So the meaning of recurrent is this particular feedback connection. If you remove this feedback connection, it will be a simple artificial neural network, right? So the major difference between RNN and ANN is around this feedback connection. Is that clear, guys? Yes, Ayushma. Just like a sequential circuit, where we have a feedback element present or memory element present. Okay. Any other questions, guys, with this part? Let me also check with YouTube, guys. Don't worry, guys, you will get attendance link by 8:30. Okay, so don't worry about it. Okay, guys, so no questions. So let me proceed with the session. Okay. So up to this point, we understood that how RNN network looks like. And if you guys just expand this network, so how this network will look like? So it's like, if you see here, guys, this is not a single input node. We have a couple of other input nodes at the back side of this particular input node, right? Same for this connection, these nodes, these connections, and these nodes. Now, if you just expand this network, you will get network like this. So what is this network? We have a number of input nodes. We have a number of hidden layer nodes and output nodes. Now, what is the recurrent? Recurrent is nothing but output of one hidden layer node, let's say H1, will be the input to the next hidden layer node as well as the current output layer, right? So this is what we are doing here. So if you see here, let's say this is at the time t. At the time t, we have this particular input. At the time t plus 1, we have this input. At the time t plus 2, let's say we have this input, and so on. So at the time t, when there is no previous nodes available, so this is the input for an input layer, and this input is being fed to this hidden layer node. Let's say this is the node H1. This hidden layer node will do the calculation, the same calculation, adder function and activation function. Whatever output is being generated, so whatever output is being generated by this node H1, it will fed to the output node of this particular time instance t, as well as the same output will be the input to the next layer node, right? So at time t plus 1, we have a second input. So this second input is fed to this hidden layer H2. Now, for this hidden layer H2, there will be two input. One input from the input layer node. The second input is from the previous hidden layer node, right? Previous hidden layer nodes. So this is the meaning of recurrent. Whatever output is being generated by previous hidden layer node, that will be memorized by the subsequent hidden layer nodes. Okay. This is one thing. Now, whatever calculation H2 will perform, in the same manner, the output is fed to the output node of at this t plus 1 time instance, as well as the output to the next hidden layer node. So in that way, subsequent hidden layer nodes will having the two input connections. One input is coming from the input layer node. Another input is coming from the previous hidden layer node. So this particular network is something we are calling as a RNN. Benefit of loop and previous slide is the only to store the out of hidden layers. The benefit of loop and previous slide is only to store the out of hidden. Actually, the representation is exactly same. But the thing is, here we have just expanded it, right? So we have just expanded this network. That's it. Okay. Is that clear, guys? How RNN architecture looks like? Cool. Okay. So if I talk about the, some real-time examples of the RNN architecture where it is being implemented. So there are a couple of, real-time examples where you can implement this RNN architecture as the application. So guys, researchers have, grouped the application of RNN into these three cases, like one-to-many kind of application, many-to-one kind of application, and many-to-many kind of application. What are these many-to-one or one-to-many or many-to-many? Let me just show you one by one. So guys, this is the example of one-to-many application of RNN, where what is a one-to-many? One-to-many is nothing but we have only one input, but multiple outputs. This is something we are calling as a one-to-many. So in this network, we have only one input, but multiple outputs. So one of the real-time example of this kind of application is, let's suppose, guys, you have this particular image and you want to generate some captions for this image, right? So the caption is a sequence of words. So in the caption, you have a number of words, but input is only a single image. So here we have a one input, which is a single image, but the output is a sequence of words, just like this. So let's suppose this image is being provided to the RNN, and it will generate the sequence of words like black and white dog jumps over bar. So here we have a, this is black is a one output, and is another output, white is another output. So we have multiple outputs. So each and every word is one output. So this is the application of one to many example, right? So one to many is nothing but where we have a one input and we are generating multiple outputs. Okay. This is one thing. If I talk about many to one, so one of the best example for many to one is a sentiment analysis. So what is a sentiment analysis? If you see, we have a sequence of words. So whatever feedback or reviews or tweets we have for different customers, so those feedbacks contain number of words. That means we have a sequence of words, which is the input to the RNN, and RNN will generate whether this customer is having the positive sentiment, negative, or neutral, right? So there is only one output, positive or negative or neutral. But the input is many words, right? So we have a many words as an input, but the output is only one, either positive or negative or neutral. So this is a typical example of many to one application. And let me also talk about many to many kind of application. So where we have a multiple inputs and multiple outputs. So one of the best example is Google Translator, guys. What it will do, you provide a sequence of words as an input in a particular language, let's say in English, and you want to translate this sequence of words into some other language, let's say French. So you have a sequence of words as an input, and you are getting sequence of words at the output, but in some other language. So Google Translator or machine translation is the best example for many to many kind of application. Is that clear, guys? These are some real-time application of generative AI. Or another example of many to many is AI chatbots. AI chatbots. So you have a chatbot which is having the artificial intelligence capability. So here you have an input box, right? So here you write your queries or your question, which is a sequence of words. And the moment you enter this query to this AI based chatbot, it will generate sequence of words as the output based upon your input query. Right? It is another example of many to many kind of application. Is that clear, guys? Any doubt or any queries? Anyone? Are you guys getting all of these things? Great. Let me also check with YouTube, guys. Okay, cool. So let's see one last but very interesting and very important concept of RNN. Okay, so up to this, we understand, guys, what is the basic artificial neural network, how the information is flowing from input layer to output layer, what are these calculations hidden nodes will perform or all other nodes will perform, And then how optimizer will try to adjust or optimize the weight values through the method called back propagation. And for back propagation, uh, at the back end, there will be uh, gradient calculation will be there. So depending upon which weight it tries to optimize, we have a chain rule of derivation, and through that it is having the number of gradients to optimize that weight. And then we saw how RNN architecture looks like and couple of real-time applications of the RNN. Now, guys, with RNN, not even with RNN, with any kind of a neural network, it can be CNN, it can be ANN, because weight optimization is, it is happening with all kind of a deep learning or AI-based models. So, especially if I talk about RNN, so there are two kinds of a problem this kind of a network will face. And it is not restricted to only RNN, as I told you. This is something very general problem with any kind of a neural network. What is the issue? There are two issues. There is something called as a vanishing gradient problem and exploding gradient problem. Let's understand, guys, what are these two issues. It's very important, guys, to understand these issues because whatever advanced architecture or whatever modified form of the RNN architecture we have, there is a link to this kind of a problem. That's why we have those modified or advanced architectures. So let's see what is the vanishing gradient problem. Let's suppose, guys, we have a network architecture like this. We have an input layer. Let's say these are the nodes for the input layer. Then we have this is the first hidden layer. Let's say this is the second hidden layer. And likewise, let's suppose, guys, we have let's suppose we have 8 hidden layers total. Or let's say we have 10 hidden layers. So this is the input layer, I1, let's say I2. This is the hidden layer 1, H1. This is the hidden layer 2, H2 node. This is the hidden layer 3, 4, 5. And let's say total we have 10 hidden layers. And then we have the output layer. Right? So we have all of these connections available. Right? All of the connections are there. And here we are getting the final output value. And based upon the output, total error is being calculated. Right? And then if I talk about the weight values, so here we have weights. Let's say, okay, let's say here we have a W1, W2, W3, and so on. Let's say here we have a W12, W13, W14, and so on. And let's pause up to here. We have a let's say W101, W102, W103, and so on. Since we have 10 hidden layers, guys, so there are lot of weights will be there. Okay. Now see, guys, if I want to optimize the weights for this kind of a neural network, where we have one hidden layer, sorry, one input layer, one output layer, and 10 hidden layers. So here we have 10 hidden layers. Just for example. So let's suppose, guys, we want to optimize these set of weights, the weights which are closer to the input layer. And if you recall how the weight optimization will work, weight optimization will always follow back propagation method. That means weights will start optimizing from the output layer to the input layer. Right? So first of all, the weights of this particular layer will be optimized. Then weights of this 10th hidden layer will be optimized, then 9th hidden layer, then 8th hidden layer, and so on. Then at the last, it will come to second hidden layer weights and then first hidden layer weights. And how the weights is being optimized with the help of the gradient calculation. So guys, if I ask you, if I want to optimize this weight W1, so how many gradients will be there? That means like derivative of total error with respect to weight W1. So if I want to, if you like expand this one as a chain rule, there will be a lot of gradients will be there. So first of all, your E total is a function of activation function of output one. Activation function of output one is a function of adder function of output one node. That is a function of this particular weight value. This weight is a function of output of 10th hidden layer node activation function, and so on. So there will be a lot of gradients will be there at the backend to calculate this particular gradient value. That means to optimize the weights for these layers, there will be a lot of gradient is being calculated. Now, as per the chain rule, all of the gradients will get multiplied. Right? All of the gradients will be multiplied. So here comes the issue of the vanishing gradient or exploding gradient. Now tell me guys, let's suppose I am calculating the E total, del of E total with respect to W1. And here I am having the number of gradients. So let's say gradient 1 multiplied by gradient 2 multiplied by gradient 3 and so on. Let's say we have a n number of gradients. So guys, if these gradient values, let's suppose all of these gradient values, if the gradient value is less than 1, let's say, for example, let's say 0.7. So if you multiply all the gradients which are already less than 1, that means very small. So what do you think, guys? The output will be a very large number or it will be very, very small number? What do you think? If I multiply n number of gradients which are very small values, that means less than 1. So the output will be, yes, so it will be, guys, very, very small and it will be close to 0. That means we are going to, optimize this weight W1, but the gradient value is close to 0. This problem is called as a vanishing gradient. That means when it comes to the, optimizing the weight values, and at the backend, when it starts, calculating this gradient, so this gradient value will get vanishes if you have a very large deep network. Right? So if your neural network is having number of hidden layers, so there might be a problem of vanishing gradient. Okay. And the similar case, let's suppose all the gradients are greater than 1. Let's say 1.2 or let's say 1.4. So if you multiply n number of gradients with this value, so the value will be very, very high. Right? You will get very large value of the gradient. That is something called as an exploding gradient problem. Is that clear, guys? What is the vanishing gradient and exploding gradient? Cool. So let's see a couple of other details with respect to these two issues. So this is what, RNN network, what we have. So one of the property of the RNN network is the weights are being shared. So if you, whatever weights you have for input layer, all of these weights will be same. Whatever weights you have for this particular layer, these weights will be same. And we are calling it as a WREC, recurring weight. And the output layer weight will be same. This is another property of RNN network. By the way, if you have this kind of a network, and if you want to optimize these WREC, right? So if you want to optimize the weights for these layers, so all the gradients will get calculated at the backend, and If the value of the gradient is very small, probably you will face the vanishing gradient issue. And the value of gradient is very large, you will face the exploding gradient issue. So this is what I have written here. Like every single neuron that participated in the calculation of the output associated with this cost function, that means the error function, should have its weights updated in order to minimize the error. That means optimize the weight value. And the thing with the RNN is that it's not just the neuron directly below the output layer that contributed, but all the neurons far back in the time. That means all the neurons towards the input layer. All those values will get updated. So the problem leads to updating the recurring weight, the weight that is used to connect the hidden layer to themselves, right? So this is the issue. So for instance, to get from xt minus 3, so let's say here we have a xt minus 3, xt minus 2, xt minus 1, and xt, right? If you want to get the output from xt minus 3 to xt minus 2, you need to multiply it with the recurring weight. Then to get from xt minus 2 to xt minus 1, again you need to multiply this input by the recurring weight. So to multiply with the same exact weight multiple times, this is where the problem arises. When you multiply something by very small number, your value will decrease very quickly, right? So if all this wrec will get multiplied, and if the value is very small, that is less than 1, the final value will be very small. This creates accuracy issue with the model. Yes. So I'm coming to this part, Nikhil, exploding gradient. Let's discuss one by one. So this is the issue with the vanishing gradient problem, right? So this is something we are calling as the vanishing gradient. So if you multiply these many wrecs, so let's say we have a 10 or 20 wrecs, which are the less than 1. So ultimately you are getting very, very small value, right? So when training a neural network using back propagation, the goal is to adjust the weights of a neural network to minimize the loss or error function. This is being done by computing the gradients of the loss with respect to the weight value, right? And using these gradients to update the weights in the direction that reduce the loss. However, in the deep network, the gradients can become very, very small, which is propagated backward through layers during the training process. So if that is the case, when your gradient is very small, and if you multiply those very small gradients, number of very small gradients, ultimately the value will quickly will become very small. That is something we are calling as a vanishing gradient issue. Now let's see, if the vanishing gradient problem is there, then what will be the consequences with your model? How it will impact your model, right? Let's quickly see that. So probably you will face two issues. One is a slow learning or stalled learning. That means if your weights are not being adjusted quickly, that means it will take more number of iteration to get the optimum value of the weight, right? So that is something called as a slow learning. Your model will slowly learn because the weight updates become negligible. Second thing, difficult in capturing the long-term dependencies, right? So generally RNNs are designed to capture the sequential dependencies in the data. So if you recall, RNN is nothing but it will replicate the frontal lobe of the mind. Frontal lobe is nothing but the short-term memory. So if your weights are not being adjusted, it will it is having the issue to capture the short-term information, which is the sequential dependencies in the data, right? So this is because the gradient needs to be propagated information through many types. Okay, so all of this information is there. So these are the two issues which the model will face if there is a vanishing gradient problem. So the solution to this particular problem, you need to initialize the weight properly. You need to use the correct activation function. Batch normalization is another approach, right? And then gated architecture. So one of the best solution to these, problem with the RNN is using the LSTM kind of architecture. So gated architecture, here we have something called as a LSTM kind of architecture and GRU architecture. GRU stands for the gated recurrent units. So these are the some updated or modified RNN architectures, which are the solution for this vanishing gradient problem. Right? Then we have an exploding gradient issue. So opposite to vanishing gradient, let's suppose we are multiplying different recurring weights, let's say n number of times. And these, these gradients will be greater than 1. So if you multiply these many gradients which are having the value more than 1, so ultimately you are getting very large value, right? So unlike the vanishing gradient problem, where gradients become very small and hinders the learning in the deep layers, exploding gradient problem involves gradient become excessively large. So in the case of exploding gradient problem, the gradients can become so large that they can lead to extremely large updates to the weight. So both are the issues. So if your weights are being adjusted very slowly due to the gradients are very small, that is another issue. And if the gradients are very large, that is again another issue to get the optimal value of the weight. So this will lead to the model instability. And they can make the training process diverge. So you won't get the optimal result, right? And why we are getting this, exploding gradient issue? Probably the weight initialization is not up to the mark. You are not taking the correct activation function, or probably the architecture design. So these can be an issue. And the solution to the exploding gradient may be, there is something called as a gradient clipping. So this involves setting a threshold for the gradient value, that please calculate the gradient value up to, let's suppose, 5 layers or 8 layers or 10 layers. Don't calculate the gradient value after this particular layer. So just put a threshold that after this layer, don't calculate the gradient. This is something we are calling as a gradient clipping. Okay. Or there's something called as a regulation method. So I'm not getting into this part. It is another approach. Proper weight initialization, batch normalization. So these are the couple of approaches. But the best solution is to use some gated architecture like LSTM or GRU. So this is what I have summarized. If your weights are very small, so the gradient will become very small, right? So this is something lead to the vanishing gradient problem. And if the recurring weights are very large, so if you multiply gradients for these kind of weights, so it will lead to the exploding gradient problem, right? So this is what we have, something called as a exploding gradient or vanishing gradient issues. Is that clear, guys? What are these two issues? So the best solution to overcome these issues are using the advanced architecture like LSTM and GRU. LSTM stands for long short-term memory. GRU stands for gated recurrent units. Okay. This is something we have with this RNN kind of a architecture. Any questions, guys? Anyone with this part? Let me check with YouTube, guys. Okay. There is one question. Vanishing is better or exploding? It's not exploding, it's an exploding gradient. Sumana, both are the issues, right? So vanishing gradient is another issue and exploding gradient is also another issue. So we need to avoid both the issues. So this is what we have discussed. The best method to avoid these issues are using some advanced architecture of RNN, which is LSTM or GRU. Don't worry, in tomorrow's session, I will show you how you can, build these kind of architectures. Okay. Yeah. So guys, tomorrow I will show you. First of all, I will discuss some, basic concepts related to the LSTM. And then I will show you how you can design a LSTM architecture and what are the different things will be there. Okay. Guys, attendance link is there in the chat box. Please check the chat box. It's there. Any other questions, guys? Anyone? Ayushman, my name is Vikash Srivastava. I'm a faculty in XLR. All right. I usually take batches related to the data science, machine learning, deep learning, and generative AI. No, no, Simona, I'm not from Bangalore. Okay, let me check with the YouTube guys. So, okay. Ayushman, that is not allowed to share any kind of a personal details, right? I hope you guys understand. Okay, guys. So, for the rest classes, like whatever sessions we left with, so the approach will be towards we will see the things related to specifically for generative AI. So as of now, we understood that what is the deep learning architecture and how the RNN things are evolved. What is the issue with the RNN and what is the solution? So tomorrow we will discuss things related to the LSTM. And if I get the time, I will also discuss something called as a sequence to sequence model, which is, one form of the generative AI technique or approach. So in upcoming classes, our focus will be more towards the generative AI applications or models, right? There is one question: what could be the asked in the upcoming test for sessions? So, guys, the test, okay. So the things will be related to the whatever you guys have studied in these 5 to 6 or 7 sessions. So the things will be related to that only. Okay. I'm not sure, Sumona. The test for tomorrow, I'm not sure about it. But if you guys follow the things, from the day one, it will be very easy. Right? Any other questions, guys? Anyone? Okay, so if you don't have any question for me, over to Amar. So if you have any question related to the study materials or LMS, you can ask Amar, right?
Yeah, sure. Thank you. Guys, I shared the attendance link. I hope you mark. If anybody is remaining, please mark your attendance. Any question for me? Let me know. Sir, I have to reply to email. Okay, Sumona, thank you. Good night. Yeah. Guys, if you don't have any query or question, actually, in sensitive exam will be beginning from this week. So wanted to know the probable date for the test. Himanshu, it's surprise test. We are not able to reveal that. Sorry for that. Guys, anything else? If no, then let me confirm once we like type it down, at least no. Sir, how to get the certificate of completed course? Don't worry, we'll explain that in the last session. I think I already explained, but no problem. But to get the certificate, 60% attendance is mandatory to make sure that you are just marking your attendance on daily basis and attending sessions as well as you're going to give the test as well. Sir, we want mobile app development certificate. Shravani, drop an email to EDL team. Team is already sending the certificates. If you're not received and if your attendance is more than 60%, definitely you will receive that within 2 days. Today send the notes. Hey guys, we are not sending a notes over the WhatsApp and email, anything. So you can check the LMS. All the materials is there till day 5. Okay. Sir, attendance link. Yeah, sure, Ritu. I'm sharing that. Can we share a screen of email to you? Sumana, what you want to say? I didn't understand. You want to say that I replied on that email, so you want the screenshot? No, not required. Hey, see, Sumana, is this your first program? Mobile app certificate, sir. Shravani, that what I repeated. We're sending the certificate, and definitely you will receive that if your attendance is more than 60%. Sumana, I don't require that. Mm, guys, I shared the attendance link. You can mark. Any another thing? Yes, no, anything? Can I have reply, please? If the assessment is not given, we will get the certificate or not, sir. It's depend upon the your attendance percent and your mark. No, no. Okay. Okay. If sir, I'm not getting the link. Which link, Ritu? Attendance link. Hey, we're sharing it on a time sharp at 8:30. We have to share because you're not going to be silent if we not share the attendance link. And me and Vikas are also informing couple of time attendance link is there. Please mark your attendance. So you have to mark that. Okay. Just make sure that you're marking your attendance. Okay. Okay. Then thank you so much, my dear participants.